Dr. D. Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to the UGC lecture series on the subject of polymers. We are dealing with the unit 2 where we are talking about the synthesis and the processes that are involved in the preparation of the polymeric materials. There are basically different mechanisms that we have seen in the earlier lectures, and today we are going to concentrate on cationic polymerization kinetics, anionic polymerization. These are the two methods we will be dealing with today. In the earlier classes we have seen the free radical polymerization mechanism and the kinetics, and later we also went around the cationic polymerization. Its mechanisms have been already dealt with, and today we are going to enter into the kinetics part of this type of polymerization, and then we will be doing with the anionic polymerization, its mechanism and the kinetics, and then finally we will be closing down with the living polymers, what are the importance about this particular polymers and their applications in the various fields. So, polymerization is basically of 3 types of polymerization mechanisms that are available: free radical polymerization or ionic. Ionic could be cationic and anionic. In the case of cationic polymerizations, the monomers which contain electron donating groups, when they are going to be attached to the ethylene molecule, they favorably undergo what is called the cationic polymerization. In the case of anionic polymerization, those monomers which contain an electron withdrawing group which is going to be attached to the ethylene molecule, they favorably undergo the anionic polymerization. Now coming to the kinetics of the cationic polymerization, let us consider A molecule as the catalyst and RH as the co-catalyst, and they form a co-catalyst-catalyst complex which can be represented by H plus Ar minus. So, initially we have to remember that in the case of cationic polymerization, a carbocation is involved in their formation and how they are going to be involved in the formation of the propagating chain and then finally a termination. Whereas in the case of anionic polymerization, it is the carbanion that is formed during the initial reaction and then it involves itself in the propagation and finally the termination. So, coming back to your kinetics of the cationic polymerization, we basically have a catalyst co-catalyst complex formed initially, and this complex that is formed as H plus Ar minus goes and attacks a monomer molecule, say M, and this undergoes an initial reaction or initiation, it is called as, with a rate constant of Ki to form Hm plus Ar minus. This is nothing but the co-catalyst catalyst complex where the monomer has got inserted into this catalyst. Further, in the propagation steps, this initiator which has formed this particular complex undergoes more and more reactions by attacking or by involving more and more monomer molecules in the polymerization reactor. So, what happens here is one more monomer adds up to this growing chain. So, this forms Mn plus 1. Further, more and more monomers enter into the polymer chain and we call it as Hm n plus 1, so many number of monomer molecules with a counter anion, that is your Ar minus. And finally, we have to end up the reaction with the termination step. So, in the case of termination, this growing polymer chain comes and attacks another monomer where there is a chain transfer taking place to the monomer and there is a neutral molecule that is formed which ends up the reaction. So, what happens here is when it attacks a new monomer molecule here, monomer alone goes and attacks and then this forms a neutral polymer molecule with Mn, where n is the degree of polymerization, number of monomer molecules present in the polymer molecule, and another growing polymer chain with an introduction or the insertion of the new monomer into the co-catalyst catalyst complex that is going to be formed. So, this is how the kinetics can be explained in terms of initiation, propagation and the termination steps. And coming to the rate of initiation, which is represented by Ri, this is given by Ki in this step multiplied by H plus Ar minus concentration, this concentration multiplied by your monomer concentration, and this is nothing but your catalyst concentration. And similar to this, the rate of termination can be expressed as Rt, which is given by rate constant of the termination, that is your Kt multiplied by the growing polymer chain. So, the rate of termination basically depends on the number of growing polymer chain or the concentration of the growing polymer chain available in the reactor vessel. So, this is given by Kt multiplied by the growing polymer chain, which is very simply represented as M plus concentration. So, Rt is equal to Kt M plus. So, having got this Ri and Rt, the above reactions, each of the propagation step basically involves what is called the carbocation, the C plus ion, which is basically very highly reactive and also adds on to another monomer immediately when there is a presence of monomer in the reactor vessel. Hence, it is not possible to find out the concentration of the carbocation that is formed at every step, each and every step in the propagation area. And it is not also possible to find out the individual rate constant with respect to the carbocation. So, what we basically do, because we cannot determine the concentration of the carbocation that is formed and which is disappearing when it is going to be taking part in the termination step, we generally go for the standard Lindman's steady state principle. So, by applying this Lindman's steady state principle, when the system is going to attain a steady state, we generally say the rate of the formation of the carbocation C plus is taken to be equal to the rate of disappearance or the destroying of your carbocation in the termination step. When we can equate this rate of formation is equal to the rate of disappearance of the carbocation, which is going to be either formed in the initiation step or destroyed in the termination step, in general, right, for the steady state Rt is equal to Ri. That is, rate of termination is equal to rate of your initiation, that is your those reactions where the carbocation is formed and those reactions where the carbocations are destroyed, that is your initiation reaction and your termination reaction. Therefore, from the above equations we can write Kt M plus concentration, that is your growing polymer chain concentration, is equal to Ki multiplied by the catalyst concentration multiplied by the initial monomer concentration. And from this equation we can rewrite the relation as M plus concentration is equal to Ki by Kt multiplied by your concentration of the catalyst and the concentration of the initial monomer, initial concentration of the monomer, which can be identified or known to the person who is doing the reaction. So, we do not have to depend on the concentration of the carbocations which are formed and disappearing during the reactions, which is not possible to be determined. So, we have this final relation for the concentration of the growing polymer chain in terms of catalyst concentration and the initial monomer concentration. Now, we also know that the rate of propagation other than your initiation and the termination, the rate of propagation which can be given by Rp is given by Kp, the rate constant for propagation, multiplied by the concentration of the growing polymer chain multiplied by the concentration of the monomer that is available, which will have to take part itself into the growing polymer chain or in the reaction. Now, substituting this first relation into this rate of propagation second relation, we have Rp or the rate of propagation is given by Kp, Ki by Kt, C concentration multiplied by square the concentration of the monomer. So, from this we understand that the rate of polymerization of a reaction which undergoes a cationic polymerization mechanism is proportional to the directly proportional to the concentration of the catalyst and is directly proportional to the square of the concentration of the monomer. So, that is what we are understanding from the kinetics of the cationic polymerization. Now, let us have a derivation or a relation for the kinetic chain length. Earlier we have understood that kinetic chain length is slightly different from the degree of polymerization. Degree of polymerization is the number of monomer molecules that are available in the final polymer molecule, but kinetic chain length is representing the number of monomer units that are present in a growing polymer chain just before the termination. So, this relation between kinetic chain length and the dP is going to be decided by the type of termination, whether the termination is occurring by coupling or disproportionation or by chain transfer. Very clearly we have seen these things in the very first type of mechanism, that is our free radical polymerization mechanism. Now, bringing that concept into the picture here in the cationic polymerization, kinetic chain length, which is represented by mu, is equal to dP when the chain termination is going to occur only by the rearrangement process. So, in this case this is given by Rp by Rt, which is equal to Kp, concentration of the growing polymer chain, multiplied by concentration of the monomer, divided by Kt m plus concentration. By cancelling these two, finally it appears to have Kp by Kt into monomer concentration. Therefore, we can say that if the chain transfer is occurring only by rearrangement, then the kinetic chain length is directly proportional to the concentration of the monomer. That is what we understand. Suppose the termination is going to occur by a chain transfer method, then the kinetic chain length is given by the dP is equal to Rp by Rtr, where rate of propagation Rp is given by Kp m plus concentration into m concentration. This is divided by rate constant for the termination Ktr by chain transfer termination, multiplied by m plus concentration. By cancelling this and this, finally it appears to become Kp by Ktr. This is equal to a constant. Therefore, we have the chain length is independent. We find that the chain length is independent of the monomer concentration. This leads to what is called a narrow molecular weight distribution. Now, if the termination is going to occur both by rearrangement as well as chain transfer, then we combine both these to get the chain length, that is your kinetic chain length is equal to degree of polymerization, which is equal to Rp by Rt plus Rtr. Once again this is given by Kp m plus concentration m concentration, divided by for Rt you have Kt into m plus concentration, and for Rtr, that is for chain transfer termination, you have Ktr m plus concentration into m concentration. Finally, this is going to be equal to Kp m concentration by Kt plus Ktr m concentration. So, this is the situation when the termination step is going to occur by both rearrangement as well as the chain transfer. Now, having dealt with the kinetics of the cationic polymerization, now let us slowly move on to the anionic polymerization. As we have already seen, monomers which are going to contain the electron withdrawing groups, when they are going to be attached to the ethylene molecule, get highly favored to undergo the anionic polymerization. As we have seen in the cationic polymerization, a carbocation is involved. In the anionic polymerization, a carboanion is going to be involved in the mechanism of the polymerization. Now, in the case of anionic polymerization, basically what is happening is an electron withdrawing group which is available in your monomer molecule this can create a positive center which can be attacked by an electron rich nucleophile. This basically creates what is called a carboanion. Let us take the example of nitroethylene. Now, if you see here, you have the nitro NO2 as the electron withdrawing group that is attached to your ethylene molecule over here. Now, this nitro group, which is nothing but the electron withdrawing group, can create a positive center, or this can influence the electrons to get attracted over here, and this carbon becomes a positively natured carbon. When this is going to be positively natured, then there is an easy attack by a nucleophile which is rich in electrons to attack this particular carbon which has become a positive center for it. So, due to the presence of the electron withdrawing group which is going to withdraw the electrons in this bond and make this carbon a slightly positive center, and this is going to be feasible for the attack of the nucleophile very easily where the electron deficiency is faced by the carbon. So, that is how this reaction is favored by forming what is called a carboanion. When a nucleophile is going to attack this carbon is going to become a carbanion. So, this carbanion is supposed to be highly active and is readily available to react with another molecule. So, this is how the anionic polymerizations are favored by making use of a carbanion which is formed during the reaction. The other examples could include alpha cyano-nitroethylene. You have the cyano and your nitro groups. You have vinylidene cyanide. You have such molecules where Y is, you have cyano as well as Y is going to be any of these COOR, COOH, CF3 or any other nitro or any other electron withdrawing groups. And another example is this molecule where Y can stand for COOR, NO2 or COOH. So, basically you have to have a positive carbon that is created within the monomer molecule because of the influence of an electron withdrawing group attached to that carbon. Then that carbon is going to be facile for the attack of a nucleophile. When the nucleophile is attacking this carbon becomes carbanion, and this is going to be very much available for the reaction to proceed with this particular mechanism called anionic polymerization. Let us have a short break and then continue. Welcome back after the short break. Now, the most commonly or generally used catalyst in the case of anionic polymerization, they include alkaline metal alkyls, alkali metal aryls, one of the example is given here, and catalysts like alkali metal hydrides NaH, alkali metal amides NaNH2, and alkali metal alkoxides. These are the various very commonly used catalysts in the case of anionic polymerization. Now, here is an example for us. Styrene basically undergoes polymerization reaction using the catalyst K plus NH2 minus, and they very easily form the polystyrene. Other kinds of catalysts could be PH CH2 minus, which also forms a polystyrene. But in the case of OH minus hydroxyl ion, it does not form a polymer. It does not undergo polymerization reaction. The reason is like this: styrene is basically a less acidic molecule, and hence it requires a more basic type of catalyst. But in the case of OH minus, it is a less basic one when compared to these two examples, hence it does not undergo a polymerization. So, there are several other factors. One important factor is this, which decides whether a polymerization can easily take place by this mechanism for a particular monomer or not. But we should also know that a more acidic monomer can easily get polymerized by a weak base. So, such an example is also possible. Now, let us go into the mechanism of anionic polymerization. Let us take the case of the monomer vinylidene cyanide. Vinylidene cyanide in a medium which acts as a chain transfer agent. Now, let us take the catalyst KNH2, which is available as a complex like this, K plus NH2 minus. When this is attacking your monomer molecule, which is your vinylidene cyanide with a double bond here, it undergoes a initiation reaction with a rate constant Ki to give a complex like this, NH2 CCN CH2 minus K plus. That means this minus has been transferred to this carbon, and this carbon becomes a carbanion. Now, this cyano group will make the carbon positive, which is basically in your monomer molecule, and this electron deficient center will be very easily attacked by the NH2 minus part of the catalyst, which is nothing but your nucleophile that attacks the carbon very easily to form a carbanion. This is a basic simple mechanism for the initial reaction. Now, let us proceed with the propagation and the termination too. So, what happens in the propagation step? Basically, I have a carbanion with a counterpart, of course, K plus ion, which is available, and this is going to be attacked by another molecule. Here you have this molecule, and this carbon is going to be electropositive because of the presence of the cyano groups on either side, and this goes and attacks your carbon anion very easily, and then the chain grows like that. So, when one monomer is added, it is the initiation. When the second monomer is added, it is a propagation, and this chain simply grows, and there are n molecules or n monomers that keeps adding to this carbanion in one particular direction. So, this becomes your n plus 1, and further it keeps moving like this. But what we generally see here is there is a movement of the minus ion portion from one carbon to the next carbon when it is going and attacking the new monomer molecule, which is coming and falling into the growing polymer chain. But this remains alive. this minus and your K plus, your counter ion keeps growing or keeps going and keeps attracting more and more monomer molecules. And this rearrangement of the ion pair in the cationic polymerization is much easier, because in the case of cationic polymerization this rearrangement is much easier because of the reason that it involves a removal of a proton or the H plus ion. But in the case of anionic polymerization, in the present case, the removal of hydride is going to be a difficult one, or it is not possible at all. So, that is the basic difference between your cationic and your anionic polymerization in the mechanism route. Now, hence the termination, because of this reason the termination by rearrangement is not going to be possible in the case of anionic polymerization. Hence, the termination occurs only by chain transfer or by suitably adding an active hydrogen compound. Now, this M minus or your growing monomer chain will take the H plus and become a neutral molecule when an active hydrogen compound is going to be present in the reactor vessel. If the medium contains an active hydrogen compound, then what happens to the termination reaction or the mechanism is that the growing polymer chain with a C minus carbanion and your K plus is available, and this ammonia molecule is your hydrogen active hydrogen compound. When such a molecule is available, this directly goes and attacks your growing polymer chain, and then the catalyst alone gets out, and then it comes out in the form of the original catalyst, and the growing polymer chain stops its growth because of the attack of this NH3 into this carbanion, and the terminated polymer is obtained there. So, this is how a termination reaction takes place in the case where it involves a chain transfer by an active hydrogen compound. Hence, whenever termination occurs by chain transfer, the molecular weight is going to be lesser. Hence, anionic polymerization generally leads to low molecular weight polymer molecules. Suppose the active hydrogen compound is not going to be present there, it is not used as a medium or a solvent, then what happens is the chain termination will not occur because of the absence of any kind of active hydrogen compound present in the reactor vessel, and each chain will be an ion pair, because we finally always have a growing polymer chain containing an ion pair containing both carbanion and the corresponding cation. So, it is always alive and it keeps growing whenever more and more monomers are added into the system. Now, having seen this mechanism of anionic polymerization, a little bit of kinetics too we are going to see now. Now, let us consider this A plus R minus as the catalyst, and it comes and reacts with the monomer molecule at the rate constant of Ki, which forms R M minus A plus, and more monomers get involved in the reaction and more M's are added, and finally we have during the propagation step R Mn plus 1 minus, of course, a carbanion is always available along with the counter ion A plus. When this is going to meet a hydrogen rich or a hydrogen active compound like ZH, the termination occurs. The termination is going to be denoted by RMNH plus your Z minus A plus. The counter ion position changes. Now, let us consider that this catalyst is K plus NH2 minus and the active hydrogen compound is your ammonia molecule. Then what happens to the rate of initiation and the rate of termination is that Ri is given by Ki multiplied by monomer concentration multiplied by NH2 minus concentration, which is the nucleophile. And coming to the R transfer or rate of termination reaction, KTR multiplied by M minus concentration, and this also depends on the concentration of the active hydrogen compound, which is nothing but your ammonia molecule in this case. Having knowing this Ri and RTR, we understand a carbanion is formed in every propagation step, and it is not going to be possible to find the concentration as well as the rate constant in each and every step of the propagation. Hence, once again by applying the standard Lindman's steady state principle, that is rate of formation of carbanion is equal to the rate of disappearance of the same carbanion, we have Ri is equal to RTR. Hence, from the above relation we can write Ki NH2 minus concentration multiplied by M concentration is equal to KTR M minus concentration into NH3 concentration. By rewriting this equation, M minus concentration can be expressed like this, and we also again know the rate of propagation is given by Kp multiplied by M concentration and M minus concentration. Now, by substituting this M minus concentration from the relation 1 in your second equation, that is the rate of propagation relation, we have Rp is equal to Kp Ki by Ktr multiplied by NH2 minus concentration M concentration divided by NH3 concentration multiplied by M concentration. Finally, we can end up with a relation like this. From this relation, we understand in the case of anionic polymerization, the rate of polymerization depends on the concentration of the nucleophile, square the concentration of the monomer concentration, and inversely proportional to the concentration of the chain transfer agent, which is nothing but ammonia molecule in this case, or the active hydrogen compound. So, 3 points we have to remember. In the case of anionic polymerization, the rate of reaction depends on the concentration of the nucleophile, square the concentration of the monomer, and inversely proportional to the concentration of the active hydrogen compound. More the active hydrogen compound, lesser is going to be the rate of reaction, or more is going to be the termination reaction. Now, we have to also describe the kinetic chain length in this case, and in this case the kinetic chain length, which is given by dP, is equal to Rp by Ktr, which is equal to Kp by Ktr, Rp by Rtr, which is equal to Kp by Ktr multiplied by M minus concentration into M concentration divided by M minus concentration and ammonia concentration. Finally, the kinetic chain length can be expressed as Kp by Ktr multiplied by M concentration by NH3 concentration. The concentration of monomer is always less when compared to the concentration of the chain transfer agent or your hydrogen rich compound. Now, so we always have a molecular weight in a lesser value, but for the same concentration of ammonia, if the monomer concentration is increased, then we can expect higher molecular weight products in this case also. Now, having seen the mechanism and kinetics of the anionic polymerization, this is an extension of that. We call certain polymers as living polymers. What are these living polymers? In the anionic polymerization, which we have seen right now, if an active hydrogen compound, which is required for the termination step, is not going to be available as a solvent, and if it does not contain any other active hydrogen compound, then the chain transfer does not take place at all. That means the reaction will never undergo a termination reaction at all. That means the polymer is always growing and it is always active, and this active ion pair that is available at the end or the terminal point of every growing polymer chain is always live, and it always allows more and more monomer to get added up to it. So, that is why such polymers are called living polymers. All the polymer chains will have a terminal ion pair, and these can be isolated by removal of the solvent and can be even stored for some time usefully. When it is freshly mixed with more monomers, polymerization will always takes place or continue to happen, and such polymers we call it as living polymers. What are the important applications of such living polymers? Basically, they are very useful in tailor making block copolymers. They are useful in the preparation of block copolymers. What is basically happening is, after polymerization with one particular monomer is over, the polymer is isolated and then treated with another molecule or another monomer molecule, which is capable of again undergoing anionic polymerization. This basically leads to what is called the block copolymer. Block copolymer is nothing but a polymer we have where you have blocks of different monomers. For example, if I have M1 and M2 monomers which is taking place in the anionic polymerization reaction, M1 blocks will be formed first, and you can stop the availability of the first monomer concentration and make the availability of the second monomer, so that this reaction continues with the second monomer, and after some time you continue the reaction with the first monomer and second monomer alternatively. So, basically what is the effect is, you can produce a block copolymer where you have two different blocks of monomers available in the same molecular chain, polymer chain. So, the size of the block can be fixed, can be tailor made by varying the amount of the monomers that are used for the preparation of such polymers. And also in terms of compatibility in blending, they can act as a compatibilizers, because you can tailor make the amount of monomers, a particular unit that is required in a polymer chain. And living polymers are best prepared generally by the solvent free conditions, because you do not require an additional step of removing the solvent. So, they are very easily or facilitatingly prepared in a solvent free atmosphere. So, coming to the summary, today we have seen about the kinetics of the cationic polymerization, and we have gone into the anionic polymerization, where we have dealt with both the mechanism as well as the kinetics, and finally an extension of the anionic polymerization, which is nothing but the living polymers, and we have seen what these living polymers are and how they are useful for preparing the block copolymers. Here are a few questions for you. In a cationic polymerization reaction, what is the basic relation between the kinetic chain length and the monomer concentration when the chain termination occurs by rearrangement and when it occurs by chain transfer, and when it occurs both by chain transfer and the rearrangement? What is a living polymer? What are its uses? Classify the following monomers into those monomers which can undergo cationic or anionic polymerization: nitroethylene, vinylidene cyanide, isobutylene. Thank you.